Hello there, I'm Andre, also known as AP-AAiS. I'm the owner of this channel, and I would like to welcome you to this first part of the second installation of the German Kid Does Something having to do with Game Boy, MIDI and the Raspberry Pi Pico series. That's right, if you haven't watched my first episode last year, I created this little thing. The MahPicoBoi interface, essentially a cost-reduced and cut-down version of the Arduino Boy MIDI interface by Timothy Lamb. In combination with a Game Boy handheld and a Game Boy software called MGB, it allows you to use your Game Boy as a MIDI synthesizer. Now, I created MahPicoBoi as part of my bachelor's degree, and all in all, the entire process really worked out well. In the end, I designed the PCB version that I've just shown you, which at this point has seen itself sold across several European countries, and really, people generally seem to be happy with what I've created, including myself for the most part. That having been said, in the last video, which introduced MahPicoBoi and talked about its entire creation process, I already identified several weaknesses that negatively affect its music creation capabilities. The biggest of these, however, is not actually specific to MahPicoBoi, but it also affects the Arduino Boy. It has to do with the fact that the APU, the audio processing unit of the Nintendo Game Boy, only mounts the hardware for 4 different sound generators. If you're familiar with MIDI, you'll know that MIDI is actually supposed to work across 16 unique MIDI channels and therefore should also be able to produce 16 sounds at the same time. So when playing back a 16-channel MIDI file, this limitation obviously makes for a pretty big problem. You're either forced to forego the use of 12 channels entirely, or you need to cut down these channels so that 16 of them will only ever play 4 notes at the same time. Obviously, neither of these two approaches make for an ideal solution, but this whole problem got me eventually thinking more in depth on this topic, and since I still had to write a master's degree for, well, my comp science master's, I eventually came up with some possible solutions for the topic of 16-channel MIDI playback on the Game Boy. Many of these solutions centered themselves around the interconnection of several Game Boy devices. After all, according to the GameLink standard, we're not actually limited to just connecting a single Game Boy to our MIDI interface. So I came up with the following plan. What if we take a Game Boy, have it run through MahPicoBoi, and then just add another one, and another one, and another one, and essentially across 4 different channels and across 4 different Game Boys, we achieved the capability of playing back 16-channel MIDI files. Well, that is exactly what I did with my creation of this first methodology for playing back 16-channel MIDI files on the Game Boy. It's called MahPicoBoi Typhon, essentially an enhanced multi-out version of the original MahPicoBoi interface. And in this video, I'll tell you all about how exactly MahPicoBoi Typhon works, how you can use it for your own music creation needs, and why it's probably not that ideal of a solution for actually playing back 16-channel MIDI files, even though it certainly works. But I'll get into the many rather severe problems which hamper the MahPicoBoi Typhon interface at a later point. For now, you can just sit back, relax, and let me explain to you how I created the first, and most likely the worst, MIDI interface for playing back 16-channel MIDI files on the Game Boy. First of all, I should probably answer the question of how exactly the multi-interface link approach to achieving 16-channel Game Boy MIDI works. Well, during my bachelor's degree, I already designed and subsequently built a Raspberry Pi Pico-based Game Boy MIDI interface that receives MIDI signals of the UART protocol at the GPIO pin GP13, converts them into the clock and serial out signals of the GameLink protocol, and then transmits those out via the pins GP3 and GP4, which should ideally be connected to a GameLink cable. From there, these signals can be sent to a connected Game Boy running an instance of MGB that will read them as they come in and convert the associated MIDI signals into instructions for the Game Boy's 4 sound generators. Now, unlike the MIDI 1.0 standard, which is built to work with up to 16 simultaneous sound generators addressed via 16 unique MIDI channels, MGB only uses the MIDI channels 1 through 5 with the hexadecimal address nibbles OX0 to OX4 and works as follows. Channel 1, OX0, is received by the first pulse wave generator PU1. Channel 2, OX1, is received by the second pulse wave generator PU2. Channel 3, OX2, is received by the arbitrary wave generator VAF. Channel 4, OX3, is received by the noise generator noise. And channel 5, OX4, is used as a poly mode. The first signal is received by PU1, the second by PU2, the third by VAF, the fourth by PU1, and so on. Because of this functionality at the side of MGB, we can only simultaneously play 4 different MIDI channels on the side of our Game Boy, even despite the fact that MahPicoBoi actually sends out all 16 MIDI channels. Additionally, whenever you're using channels 1 to 4, you should ideally avoid using channel 5 entirely, since it will otherwise cut off the dedicated generator signals for PU1, PU2, and VAF. Now, the question we obviously want to ask ourselves is, how exactly do we bypass this limitation on the side of MGB? Well, since the hardware of the Game Boy only contains 4 sound generators, we obviously can't expand MGB in a way that would allow us to simultaneously play the notes of all 16 MIDI channels on a single Game Boy. One simultaneous note per sound generator is a hard limit that we can't reasonably bypass. So, to play additional notes, the only option that we're left with is to add additional Game Boys to our system. The easiest way to do this would simply involve hooking up additional Game Boys to a multi-out GameLink cable of our interface, or by first connecting entirely new GameLink cables and then hooking up additional handhelds to those. This is easier said than done, however, since we then have to ask ourselves the question of how exactly our interface is supposed to determine which Game Boy and which generator of that Game Boy responds to the signals of which MIDI channel, and what part of our system deals with the determination of this channel to generator mapping. Of course, our system includes at least 2 entirely different processing units that could, realistically, both do the job similarly well. We could either use the RP2040 microprocessor of our Raspberry Pi Pico or the SM83 CPU of a Game Boy. Now, since the RP2040 CPU at the heart of the Raspberry Pi Pico is both significantly faster and significantly easier to work with than the Game Boy's old SM83 CPU, this first multi-interface link method will detail the steps needed to get all necessary channel recognition and distribution algorithms working on the side of our Raspberry Pi Pico. Right at the beginning, if we want to use the Pico to determine our channel assignments, we immediately run into a new issue. Since we'll be using the stock version of MGB, each Game Boy of our system only uses the MIDI channels 1 through 4 in order to address their 4 APU sound generators. Accordingly, we will need to map the MIDI channels with a hexadecimal address greater than OX3 back into the range of OX0 to OX3. But if we simply use a modulus operation to do so, we would remove all discernibility between, for example, the signals of the MIDI channels 1, 5, 9, and 13, since they would then all use the same hexadecimal MIDI channel address of OX0. If we were to execute such a channel remapping algorithm and then simply send out the converted signals via multi-plug game link cable that has multiple Game Boys connected to it, all Game Boys of our system would inadvertently always play the same notes. Furthermore, the different MIDI signals of a channel range that has been assigned the same address by the Raspberry Pi Pico would still cut each other off, so this approach would, obviously, grant us no tangible benefit to the Game Boy's MIDI playing capability whatsoever. So, to make sure that each Game Boy receives only those signals that are relevant to the 4 sound generators mounted on its APU, we will need to electrically isolate the game link cables of each handheld. Thus is born the name and methodology of the multi-interface link approach. In truth, the multi-interface link approach to 16-channel MIDI playback on 4 Game Boys is actually rather simple. Since my previously developed MahPicoBoi already introduced an algorithm to send out all 16 MIDI channels via the GPIO pins GP3 and GP4, all we'll need to do now is to define 6 new GPIO pins that will be used to transmit the isolated signals to the 3 new Game Boys of our system. To make things as simple as possible, I've decided on using the following GPIO pins. Just like on the original MahPicoBoi, the pin GP3 will send out the serial signals to the serial in pin of the game link connector of our first Game Boy, while the pin GP4 sends the corresponding clock signals to the clock pin. Similarly, pin GP6 will transmit the serial in signals of our second Game Boy, while pin GP7 carries the needed clock signal. Pin GP8 carries the serial in signals and pin GP9 the clock signal for Game Boy number 3. And finally, pin GP10 carries the serial in signal for the 4th Game Boy, while pin GP11 carries its clock signal. Beyond the clock and serial pins, the ground pins of each game link connector will also need to be hooked up to a G&D pin of our Raspberry Pi Pico, but you're essentially free to choose whichever G&D pin you like. The process by which you connect these pins of a Game Boy Game Link connector with the appropriate pins of a Raspberry Pi Pico is also entirely up to you. In most cases, you'll be best served by modifying a Game Link cable to do so. The appropriate modification of a Game Link cable will require you to cut off a Game Link connector at one side, at which point you'll peel off the rubber isolation of the cable. Inside, you'll find several smaller cables, each isolated from one another, that will further need a small section of their isolation stripped so that the internal copper strands can then be connected to the GPIO pins of the Pico. At this point, I'd highly recommend you to use a green Game Link cable of the type shown in this picture. They're not only cheap to get, but also offer you both an original Game Link connector as well as a smaller Game Link connector introduced with the Game Boy Pocket that you'll need if you're using a Game Boy Pocket, Lite, Color, Advance, or Advance SP. Furthermore, the manufacturers of these cables seem to always use the same colors for the rubber isolations of the internal cables, which means that you can extract the functionality of an internal cable that belongs to one of these green Game Link cables simply by checking the color of its isolation and consulting the following table. Now that you've got the appropriate internal cables at hand, it's time to hook them up to the Raspberry Pi Pico of our MahPicoBoi setup. Depending on the version of MahPicoBoi you own, there are several different methods available to you. If you've built a MahPicoBoi on a breadboard, you could use either several DuPont connectors or a 2.54 or 5.08mm screw terminal. If you own a pre-built MahPicoBoi, you'll most likely just want to solder the exposed copper parts of the wires, just like I did. Once all cables of the GameLink connectors are wired up to the MahPicoBoi, you're pretty much ready to run the new MahPicoBoi control software that contains the necessary changes to automatically take care of the channel generator Game Boy assignments. I've given this new software the name MahPicoBoi Typhon, after the Greek god of Typhon with his 100 screaming snakeheads. The next part of this video will detail the inner workings of the software for those interested. If you've already compared the source code of MahPicoBoi Typhon to that of its predecessor, you'll know that this project really didn't require the implementation of any great software additions to gain its ability of working with multiple receiving Game Boys. The few noteworthy changes that were implemented are also all rather marginal in terms of their complexity and can therefore be explained fairly quickly, which is why we can get started on our examination of the new source code without further ado. Should you have any questions about the functionality of the base MahPicoBoi project during this part of the video, I recommend you to either read the documentation provided within the MahPicoBoi GitHub repository or to watch my previous video on the development of this Raspberry Pi Pico-based Game Boy MIDI interface. Now, first things first, to get our Raspberry Pi Pico control software working with the additional GPIO pins of our 3 new Game Boys, we'll first need to take care of some defines that provide us with some set values that we'll be working with later on. First, we'll define each GPIO pin used in our system individually, so that we have a dynamic reference to the values for which the pins will be initialized and addressed later on. Next, we'll need to figure out the way in which we assign the signals of a MIDI channel to its own APU generator. For each channel, we'll need both a value to represent its intended target generator, as well as a value to designate its intended target Game Boy. To send out the signals of a Game Boy via the correct GPIO pins, we'll obviously always need to know the position of the correct serial in and clock pins. Since the serial in and clock pins of each Game Boy are seated right next to each other in my development build, the following code will only ever need the location of one of these pins to automatically be able to determine the location of the other. Accordingly, I've chosen to define each Game Boy of our system by the location of its serial in pin. Next, we'll need to define the generators of our system. As MGB uses the MIDI channels with the hexadecimal address values of 0x0 to 0x3 to communicate with the 4 generators of a Game Boy's APU, we could simply use these values to take care of the assignment that way. However, as you can see here, I've actually decided to define each generator by its MIDI channel address shifted 4 bits to the left. This odd way of saving the channel values allows us to make use of a neat little trick. Since the defined values of all 4 serial pins within our system sits in the range of 4 to 10, they can each be comfortably saved within a single nibble, or 4 bits, of data. Similarly, the MIDI channels of our generators also only sit in a range of 0 to 3, meaning they can easily be stored within a single nibble as well. By shifting our channel defines 4 bits to the left, we can save both the Game Boy define as well as the channel define in a single 8-bit value simply by adding the two together. We can make use of this functionality within the following 16 defines for all channel Game Boy generator mappings. Each assignment simply consists of the value of a Game Boy, GB1 to GB4, plus the value of the target generator. As this piece of code shows us, we can, for example, designate that MIDI channel 16 plays on the noise generator of Game Boy number 4 by simply defining channel 16 targets as GB4 plus noise. With these defines in place, we've actually already taken care of all the initial channel assignment work. Next, we'll need to deal with the actual transmission of our signals. To do so, we'll first have to initiate all 8 output pins that we've previously defined for digital out transmission. Additionally, we'll pull all clock and serial signals of our system to their electrical resting point level. For our serial in pins, this level would sit at a logical low at 0 volts. And for our clock pins, that resting point would sit at a logical high of 3.3 volts. At this point, I should probably mention again that the GameLink protocol, by its definition, is actually supposed to receive and transmit data at 5 volts. However, during the development of MahPicoBoi, I just happened to stumble upon the discovery that 3.3 volt digital signals work just as well and do not actually require a level shifter. But regardless of such electrical minutiae, we can now get into receiving, translating, and transmitting our signals. Most of this process hasn't changed much from the original MahPicoBoi source code, so I'll only highlight a few changes here. First, since we'll need to retain the target serial pin for all bytes of a MIDI signal, despite only the first status byte of a signal containing the MIDI channel address, I've declared a new 8-bit pointer variable that will save the assignment for the duration of a MIDI signal transmission. We'll hand this pointer over to the readRx function, which contains the following new code. After having read a MIDI byte from the Raspberry Pi Pico's UART0 input buffer, we'll use the previously assigned variable bytes sent to determine if our read byte is a status byte. Byte sent is always 0 while we're reading a first byte of a MIDI message, so all we have to do is check if byte sent is presently 0. Should byte sent indicate to us that we are in fact dealing with a status byte, then we'll need to recalculate the target serial pin and target generator of the coming signal. To do so, we'll first get the original MIDI address of the current signal through a bitwise AND operation between the MIDI status byte and a byte of the hexadecimal value of OXOF. The resulting byte will be stored in a new variable called address. With the original signal address on our hands, we'll call a function called getTargetSerialPin and channel, which takes the address value and uses a switch statement to return the appropriate channel X target define value. That value will be stored in the reference target serial pin and channel pointer for the next data bytes that follow. Now that we know which generator the current signal is actually meant to talk to, we'll have to substitute the original address of our status byte with the address stored within the target serial pin and channel pointer. This is achieved by first extracting the address via bitwise AND operation, which removes the value of the target serial pin from that pointer, and then we shift that offset address back 4 bits to the right. The resulting value represents the actual target MIDI channel of our signal, which we'll momentarily save in the address variable. Next, we'll use another bitwise AND operation to remove the original address from our status byte, followed by a bitwise OR operation to add the true address back into the byte's value. Finally, we're in possession of a byte that we actually want to send out to one of our Game Boys. To do this, we'll call a slightly modified sendMIDI2GB function that not only takes the byte to be sent, but also the target serial in pin that should transmit the byte's data as arguments. To get this target serial pin from our target serial pin and channel pointer, we'll simply have to dereference it and then remove the value of the target channel via a final bitwise AND operation. Now we'll transmit our byte to the Game Boy. To do this, we'll follow the same procedure from the original MahPicoBoi control software, which works as follows. First, we'll pull our clock signal from its resting level of 3.3 volts high back down to 0 volts low. Then, we'll send out the rightmost bit of our byte. If that bit is a 1, then we'll pull our serial in pin to a logical 3.3 volts high. If it is 0, then we'll pull our serial in pin to a logical 0 volts low. Next, we'll pull our clock pin back to its resting point of 3.3 volts high, so that our Game Boy knows that its serial pin presently sits at a correct level, which should be read as a bit. Afterwards, we shift all bits in our remaining byte 1 bit to the left, and then repeat the above procedure for all 8 bits of our byte. Now, since this new send MIDI to GB function has already been given the value of the serial pin that we would like to transmit our data over, we can simply calculate the position of the corresponding clock pin by adding a 1 to the serial pin value. Thus, we are now in possession of the locations of both pins, as well as an appropriately altered byte. We can now simply transmit each MIDI byte via the procedure just described above. With that, the entire process for determining the targets of a MIDI channel has now been implemented. And that's it. Really, MahPicoBoi Typhon doesn't make for that complex of an expansion to the original MahPicoBoi project. If you know a thing or two about working in C or with MIDI, I'm sure that you'll have had little issue following along with the code changes I've just described. But regardless, now that we've discussed the functionality of this new software, we can finally get into the topic of how you can use MahPicoBoi Typhon for your own Game Boy music composition needs. For the most part, you can use the multi-interface link system and MahPicoBoi Typhon in exactly the same way as the original MahPicoBoi project. I'll give you a very brief overview in this section, but I recommend you either watch my original MahPicoBoi video or read through the build guide on my website to get more information on how to use both MIDI interfaces. As a first step, you'll need to load the MahPicoBoi Typhon UF2 file onto the Raspberry Pi Pico. You can download this file from the project's GitHub repository. To load it onto the Pico, you'll have to connect the microcontroller to a PC while holding down the boot cell button, and then drag the UF2 file onto the Raspberry Pi Pico storage device. For the remainder of your active usage of MahPicoBoi Typhon, you'll have to keep the Raspberry Pi Pico connected to a power source via its micro USB port. You'll know that it's correctly running the MahPicoBoi Typhon code when the green LED lights up. Additionally, you can press the boot cell button of the Pico during playback to block MIDI CC signals from being sent to the Game Boy. Unknown CC signals can and oftentimes do corrupt the RAM of MGB, so it's best to keep CC signals blocked when you're playing a generic MIDI file. Just like with MahPicoBoi, the MahPicoBoi Typhon's LED will flash in regular intervals while CC signals are being blocked. Next, you'll have to connect the 2 MIDI plugs of the cable to your MIDI source with the 2 MIDI terminals of the MahPicoBoi Typhon. Connect the MIDI out plug with the MIDI in terminal and the MIDI in plug with the MIDI out terminal. Now, connect up all the Game Boys of your system to the new Game Link cables of your MahPicoBoi Typhon. Once the Game Boys are connected, you'll have to run a version of the Game Boy software MGB for a Game Boy or Game Boy Color Flash cartridge on each Game Boy you would like to play your MIDI signals. With that, your MahPicoBoi Typhon is ready for MIDI playback. Simply play a MIDI file or send out MIDI signals from your MIDI source, and MahPicoBoi Typhon will automatically send the signals of a MIDI channel to a unique generator on one of the 4 Game Boys. By default, MahPicoBoi Typhon uses the following channel mappings. MIDI channel 1 addresses the PO1 generator of the first Game Boy. Similarly, the MIDI channels 5, 9, and 13 address the PO1 generators of the second, third, or fourth Game Boy. The MIDI channels 2, 6, 10, and 14 address the PO2 generators of the first, second, third, and fourth Game Boy. The MIDI channels 3, 7, 11, and 15 address the WAV generators of the first, second, third, or fourth Game Boy, and the MIDI channels 4, 8, 12, and 16 address the noise generators of the first, second, third, or fourth Game Boy. You can change these channel assignments by altering the different channel X target defines within the MahPicoBoi Typhon.c file. However, the change of these defines requires you to recompile the MahPicoBoi UF2 file, which, in turn, requires you to set up both the Raspberry Pi Pico C, C++ SDK, as well as CMake. You can decide for yourself if that's worth the effort. Also, there's presently no way for the channel assignments of MahPicoBoi Typhon to be altered during playback. Obviously, this makes the multi-interface link system in its present shape not only very difficult to set up, but also not all that versatile when you're working with it. In truth, the multi-interface link methodology had originally been conceived as the simplest way of getting 16-channel MIDI working across 4 Game Boys. After all, it allowed me to work with the Raspberry Pi Pico SDK, which I was already very familiar with, and only required some minor hardware modifications. Yet, from a consumer standpoint, MahPicoBoi Typhon is incredibly cumbersome in both its deployment and usage, especially when compared to the single interface link method, which I'll introduce in the next video on the topic of 16-channel MIDI playback on the Game Boy. It solves pretty much all the versatility problems of the multi-interface link method, while also requiring far fewer hardware modifications. Yet, despite all of these shortcomings, there's still at least something positive which can be said about MahPicoBoi Typhon. For one, it works, for the most part, and secondly, you can use pretty much whichever MGB version you want with it. Meanwhile, the later on single interface link methodology is locked to using MGB Hydra only. That's about it in terms of positives, and I really don't expect these two aspects to offset the cost and dedication of having to attach or even solder additional game link cables to most people. It really doesn't even do so for myself, if I'm honest. Now, as a software developer, it's kind of hard for me to abandon or disown any of my projects. In the software world, we love all of our impressive fuck-ups, or happy little accidents as Bob Ross would call them, even if they end up grounding all international air travel for a day or 3. That having been said, when you create a piece of software which is just strictly superior to another piece of software in all relevant aspects, well, then at some point you're left with no other choice but throwing the baby out with the bathwater, together with the bath, the shower, the rest of the bathroom, the dog, your wife, maybe even yourself. And this is exactly one of those cases. Accordingly, I'd still like to thank you for your dedication of watching this little documentary about a piece of software which was deprecated well before its official release. As a small reward, I'd like to leave you with a final piece of music played through the multi-interface link system, which I hope you'll enjoy. If you'd like to learn more about MahPicoBoi Typhon and the multi-interface link methodology, you can check out the GitHub repository, which I've linked down below. And if you'd like to get your own hands on a MahPicoBoi PCB to build your own multi-interface link system, you can check out the eBay page, which I've also linked down below. Otherwise, I hope I offered you at least some insights of value and wish you a truly awesome rest of your day. This is AP, signing out. Have a good one.